Now that I expressed the concept of what we are going to do, we can give a look a little bit of physics. And to do that, let's recall first what is the scenario we are working with, meaning we are going to consider a spherically symmetric object with a certain density which is constant across the entire body, which is going to be rho A, and all around the body we are going to have a uniform background with density rho B. Okay, so this body is not in vacuum, but there is a background. We are going to perform various approximations in the process. For example, you know that we should use a metric which is the surrounding of a massive object. If rho B is much smaller than rho A, we could use the Minkowski metric or something very similar. That's because Minkowski metric is valid in vacuum. Here there is no vacuum, but roughly. Okay. In any case, we are going to neglect even this back reaction, and we are just using Minkowski spacetime surrounding the body. That's because I want to avoid complications, mathematical complications that are not necessary to highlight the key concept that we are going to discuss. Okay? Keep in mind, spherical massive object, constant density, and embedded in a uniform background, and I'm going to do various approximations that I will spell every time that we encounter them. Okay? Good. So, what is going to be the equation of motion once we have this coupling? Coupling that ends up to appear in this conservation law. So we have the conservation law for matter, we have the conservation law for the field phi, and yeah, I say conservation law, but actually both the energy momentum tensor of matter and field are not conserved because there is a coupling term popping up here. Remember that the two were the same amplitude with a minus of difference because it was they are expressing the energy momentum exchange between matter and the field. That's something that we have seen. Good. Now I want to look for the equation of motion, given the existing of this coupling term, and to do that we look for the continuity equation, if you wish, the Klein-Gordon equation, that is found by setting nu equal to 0. Okay, so that's this expression with nu equal to 0, and the two expressions read like that. This is for matter and this is for the field phi. The solution of this expression is trivial, that's something that we already did in the previous lecture, and the solution of this expression is this one. This one, that again, as we already did in our previous equation, in our previous lectures, can be rephrased in this way by introducing this density, which now has the meaning of particle mass, which is evolving as a function of time as the universe is expanding. Then the other thing that I did was to relabel our potential just to phi. So phi minus phi dot can be equal to 0. I can do that, so this is not really an equality, but this expression and this expression give rise to the same equation of motion. That's why we can do this relabeling. Okay, again, proper, this equal is not correct, strictly correct, but just keep in mind that I just did a relabeling of the potential such that this guy gives rise to the very same equation of motion. Then we look for our Klein-Gordon equation for the field, so the equation number 2, that can be rephrased in this way once we plug in the definition of rho and p here, here, and here, where rho and p are the one of our fluid. Remember that the equation that rho for our field phi is equal to 1/2 phi dot square minus the potential, and the pressure instead is equal to 1/2 phi dot square, where actually there is a plus minus v. Okay, so we just use these two expressions and we plug them here. Whenever we do so, this equation 1 reads like that. Then the other nice things that we can do is to bring this guy and pull it on the other side of the equation in this way. Okay? And define this v, phi plus Q rho as the derivative with respect to phi of an effective potential, such that now we have again the Klein-Gordon equation, but the coupling has been absorbed in a potential, an effective potential, which is going to characterize the equation of motion of our field, and therefore the properties of our field. Look, now something that I'd like to stress is that this phi, this potential contains the density, and it tells you that the field is going to behave differently in regions where rho is large or rho with respect to regions where rho is small. And therefore the field is going to behave differently in dense, in overdense or low density regions, okay? Which is one of the key features that we want to introduce in our theory, and see if we can then pull out a screening mechanism, the screening mechanism that I mentioned. Moreover, if we are using the definition of our potential, look that this is just that, this is just this expression, we just perform an integral of this expression and we obtain this. Okay, so we have an explicit expression for our potential. I mean, we have the derivative, we integrated once, we have the explicit expression for the potential. Nothing, that's very simple and trivial. Good. Then the other thing we can do, nice, we have our nice new Klein-Gordon equation with our effective potential. What we can do is to express our box operator in an explicit form, and we can do so because we are considering a spherical symmetric object, right? Therefore we can use spherical coordinates. Moreover, we are using a weak gravity background, therefore we can neglect back reactions, and as a background we can use the Minkowski space and neglect the time derivatives. So basically we are neglecting the retardation terms in our equation. Therefore our box phi reads like that. And a little bit of mathematical reshuffling, this expression can be written in a more compact way like that. Okay, to convince that this guy and this guy are the same, do it the way around. Just apply the derivative to that and you will find this expression. Nothing more complicated than that. Okay? And with that, we have our Klein-Gordon equation expressed in this way. So this guy is this expression in spherical coordinates, assuming a weak gravity background. Okay? These are the two equations, Klein-Gordon equations describing matter with its solution, and the equation expressing the field describing phi that we can rewrite in this way.